Okay, a couple of sentences about me. My name is Moritz. You can find me on GitHub as Molen. I'm a reliability engineer at Form3. I'm in the platform infrastructure business line. We manage Kubernetes clusters across multiple cloud providers in the data center. We manage network equipment in our data centers and a lot of stateful workloads such as CockroachDB and NUTS. I'm also one of the original creators and maintainers of external secrets. So if you want to talk about secrets management in general or all things reliability, just come around. The agenda for today, so before we dive into the cross-cluster pod disruption budget thingy, I would like to provide you a little bit of context about Form3, about how we run infrastructure. That's very important context for the problem that we're trying to solve here. And before we go into the XPDB thingy, I'll like to tell you about some the basics about pod disruption budgets, the eviction API, and all of that. So what is Form3? Form3 is a financial service provider. We're a B2B business, a bank-to-bank business. Banks generally want to send money, and we provide them a unified API so they can send money. We integrate different payment schemes like FPS here in the UK, but also SEPA in the EU, and also a bunch of others in the US as well. So a couple of sentences about the infrastructure. This is like a really, really high-level overview of how our clusters look like. For us, we always run our clusters in a stack. That's what we call it. So here, each box is one cluster. One runs in Amazon Web Services, one in Google Cloud, one in Azure, and they're all connected with each other. So the pod networking is flat. Every pod can talk to every other pod. We have cross-cluster DNS resolution, so some pod in EKS can resolve a DNS record from GKE or an AKS cluster. And we also run a bunch of stateful workloads that are very important for our payment processing. One is CockroachDB, the other one is NUTS. That's where we store our data and have our data streams. We do multi-cloud, so we integrate multiple cloud service providers, and also we run stuff in our own data centers. It is more complex than that, the reality, unfortunately. So we have this multi-cloud world here on the left-hand side, that stack of clusters. But there's another stack of clusters, which are slightly different, but also similar. The vertical one on the right-hand side, that's where we have two clusters in two separate data centers here in the UK, here on the corner, and also one running in EKS. And this is also a stack of clusters, but it's slightly different. And that stack on the right-hand side, that provides access to the payment scheme. That's where the actual magic happens. Of course, it's more complex than that because we run different, multiple environments, development, integration, staging, production, both in our multi-cloud world and also in our data center world. And also we connect to different payment schemes. In fact, for some of our biggest customers, they run on dedicated infrastructure, so they have their own stack, or their own stacks rather, where they then can do load testing in the staging environment or have their own production environment, and it's completely isolated and dedicated for them. It is more complicated than that, to be honest, because this is roughly what we run in the UK. We run more stuff in the US and in Ireland as well. But I didn't want to, prep a slide for that. That wouldn't make a lot of sense. So for today, we just need to look at that because that's the core unit we need to take into consideration. So about PDBs in general, that's what a PDB looks like. Can we do a quick show of hands who knows what a PDB is? Everyone? Mostly everyone. Good. Quick refresher on that. We have this max unavailable field. What does available actually mean under the hood? It means that a pod passes the readiness probe. That's it, basically. So when a pod is not ready, then it does not get more connections from the Kubernetes service object, and is not considered to be ready in the context of a pod disruption budget. The eviction API is just a simple Kubernetes API endpoint, which in the end terminates a pod. So it's similar to the kubectl delete pod API. But before the pod is terminated, a the pod disruption budget is verified, and if that eviction would cause more harm and would violate the PDB, the kube API server would respond with an HTTP 429. So that would indicate to the caller that he's supposed to come back at some later point. Let's have a quick example here. So we have 3 pods on the right-hand side. All of them are ready and healthy, and I can try to evict the one on the left-hand side. That would work, no problem. If one pod would not be ready, the one on the right-hand side, and we try to evict the one on the left-hand side, that would not work because our max unavailable setting is set to 1. One is already unready, so we are not able to evict another one. Easy. If we were to evict the one on the right-hand side, that would work, simply because it wouldn't make the situation any worse. And as everyone knows, simply restarting a node, restarting a pod sometimes solves the problem. So we can do that without issues. But there's a little bit more to it. When you take a look at the Kubernetes documentation, you can read about voluntary and involuntary disruptions. Voluntary, these are the ones that are done by Kubernetes administrators, like draining a node, moving workloads somewhere else, or engineers who deploy a configuration change, deploy a new image version. That's that. But in terms of involuntary disruptions, there are like many sources. Just recently, like a month ago, Amit Balkan, I think he's a well-known figure here in the Kubernetes community, he released a blog post on everything around involuntary disruptions, and I just grabbed this table from his blog. So go check that blog out. It's like very, very helpful to understanding involuntary disruptions. As you can see, I hope you can see it, on the very top, there's this eviction API. That's where that's called when you use kubectl drain. That's like pretty much the only API call that respects the PDB, and most others do not respect that. So a direct pod deletion like kubectl delete, or a workload controller like a replica set controller, the daemon set controller, deleting pods, they do not respect the PDB. However, they implement their own readiness checks, so they wouldn't cause any harm in a single cluster context at least. And a bunch of others like node pressure, priority, preemption. There are a lot of involuntary disruptions. So why am I doing this talk? Because it's not that easy if you have a multi-cluster topology, where you run into issues when you have one workload spread amongst different Kubernetes clusters. Again, this is our world with this stack of clusters, one in EKS, one in GKE, one in AKS, and we have 3 replicas of CockroachDB running in each cluster. Now, let's take a look what happens if the one here in GKE, the CRDB2 pod, is not ready, and we're trying to evict the one in EKS here on the left-hand side where the arrow points at. That would work without a problem, because PDBs aren't aware of what is happening in this other cluster. Like, of course, how would it be aware of that? In our context, this is a problem because CockroachDB under the hood has a raft group. They have a leader election raft group implemented. And in this case, if 2 pods would go down, like 2 wrong pods that host this range 1, 2, 3 that is displayed here, in that case, you would lose the majority of your pods, and as such, you would lose the leader, and as such, this database range would not be available anymore. So for us, there would be a P1 or P2 kind of incident immediately because some database records are not able to be read or to be written to. There are a couple of contributing factors that you typically see when you have lots of movement in your clusters. That was like our major problem. Having like lots of clusters, you can work around this issue that I just showed you. But if you have like lots of changes coming from configuration changes or rolling out changes to CockroachDB or to Nats, or if you do regular node maintenance, I guess everyone here does regular updates to the nodes, updating the kubelet, the Kubernetes version, updating the kernel and all of that. We do this like on a regular basis, and our development and integration stacks, we do this like once a day. Like all that movement kind of contributes towards that issue where you potentially just shoot the wrong pods and then you have an incident that you got to resolve and work on. On top of that, we run a bunch of more stuff, chaos experiments, we do incident rehearsals like every week, and like a bunch of other stuff that can happen to your clusters that could make the problem just more prevalent. How can we fix that? Well, we can just coordinate and communicate and manually check the state of our workloads before we deploy configuration change, before we drain nodes. But this is really a big pain, and it doesn't scale with the number of clusters. It doesn't scale with the organization. We tried this in the past, and it didn't work. It never has worked, and the whole process was just doomed to fail. So we automated that away and made that work for us. So what we really wanted is a pod disruption budget that spans multiple clusters. So in our perfect world, we imagined, if we try to evict the pod here in EKS, the middle one, CDB1, we would just be able to somehow block this eviction from happening because we need some mechanism that is aware of all the replicas of CockroachDB across all the clusters. That's what we did. Pretty simple and straightforward. We open sourced this tool. You can take a look at it. Unfortunately, InfoSec doesn't allow us to provide contain images for you, so you got to build it yourself, but at least that's something that you can take a look at if you also suffer from the same problem. Maybe we can do a quick show of hands. Is anyone here suffering from like multi-cluster topologies, or are we the only idiots? Oh, you too? You too? Great, cool. That's why you're here. Cool. I'd like to hear how you manage these kinds of problems. It's a real pain in the ass. Okay, so what did we do? Essentially, we hijacked the eviction API by using an admission webhook. So whenever there's a evict pod API call, we would just hijack that, take a look at all the replicas in all the known clusters, and then we can make a decision. Either thumbs up, yeah, sure, you can delete or evict that pod, or thumbs down, and respond with the same thing, HTTP 429, please come back later. Yeah, that's it in a nutshell. When we take a closer look, we also implemented our own custom resource. Here on the right-hand side, the X pod disruption budget, which is like a cross-cluster pod disruption budget. And as you can imagine, it looks pretty much like a pod disruption budget, but is aware of all the clusters and all the pods. And we have added a bunch of extra fields, which we might come back to later. So how does it work in detail? Looking at the left-hand side, so when something calls the eviction API, that could be a kubectl drain, that could be some operator that runs in your infrastructure that manages and maintains your node pools and moves the workloads off to other nodes. Now this eviction API comes in, then this admission webhook is sent to xpdb. That's our controller that runs in every cluster. This is a controller and is a webhook server, so it receives the admission webhook, and then it fans out to all the known clusters and says, okay, look, what is your state of the world? How many replicas are you supposed to have? How many replicas do you actually have? And how many of them are ready? These are the three key things that we need to know from each and every cluster. And with that, we have all the information, all the state of the world to file a verdict, and then can say a thumbs up or thumbs down to that eviction call. It is slightly more complex than that because we need to deal with a race condition here. Potentially, we can evict one CockroachDB pod in EKS and simultaneously in GKE as well, and potentially like in all the clusters. To work around this issue, we've implemented a locking mechanism so that whenever a admission request comes in, we acquire a lock that is under hood just a lease object, and we hold this lease, which is specific for this admission request, that is specific for this particular workload and this particular namespace. So we hold this lease for 5 or 6 or 7 seconds, and then we fan out and ask the other clusters, hey, what's your state? And then they themselves also acquire this lease, acquire this lock, and hold it for 5 to... Are we in power saving mode? Okay. And then they themselves hold this lease and send the response back to the original caller, and then we send the admission response back to the kube API server. There's a little bit of an overhang, so we hold the lease slightly longer than the admission webhook is in flight, because when we return the response to the admission webhook, we still got to hold the lease because the kube API server is still processing the request, and there's still a potential that a race condition could occur. Yeah, that's what we did. So in this case, again, the same picture. So one CockroachDB pod here in GKE is unavailable and trying to evict one pod in EKS. We would just simply block that because of what I just told you. There's one more thing to note here. We have this X pod disruption budget deployed to each individual cluster because there's no concept of this like a cross-cluster custom resource or custom resource definition that just doesn't exist, so we cannot have that. Instead, we have one XPDB resource deployed to each individual cluster. What about involuntary disruptions? I showed you the table earlier, and only the PDB was respected in the eviction API call. So direct pod deletion would not respect the PDB, but in our use case, if a replica set would trigger a change in EKS and something would be unavailable in GKE, it would not be aware of that. So we also have to take care of the of the pod deletion API call. So we also hook into that one and implement the very same logic here. So in the end, we end up with this table here where the PDBs are respected in every case, in every pod deletion, when there's node pressure, when there is a preemption due to pod priority, we all block those. That's just based on our requirements because we cannot delete a particular pod that is part of a RAF group. And in CockroachDB, we just need to prevent that at all cost, basically all cost. This has been running in production for about a year now, so it works with that configuration. Actually, for the preparation of this talk, I just revisited that. I reflected what we've implemented, and I found like, damn, there's still this node deletion garbage collection going on. Is that a problem if we cycle the nodes, but we have this pod disruption budget? But apparently it's not a problem. It's fine. So feel free to try this out in production. It probably works. What could possibly go wrong with this? So as with every admission control webhook that you have, there are a couple of issues that you need to take a look at. One is if the admission webhook server is unavailable. So if XPDB is unavailable in a particular cluster, we would block every call to the eviction API and every call to a pod deletion. So that's not a place that you would like to find yourself in, because that could potentially lock you out of the cluster or cause some other issues. We've worked around that problem by implementing label selectors on the admission webhook resource, so that only specific pods from specific namespaces are subject to the interception of the pod deletion and pod eviction API call. So only if a pod is deleted in the CockroachDB namespace, like we care about it, and everything else, kube system namespace, we do not hijack the eviction and pod deletion API call. And there's a second failure scenario where the remote cluster's XPDB server is unavailable. In that case, we just need to manually take a look at the state of the world and see if we can fix that temporarily, or we want to take that remote server out for maintenance. Just in case there's a regional outage or some bigger issue with a particular cluster, we just need to take it out of the equation when taking a look at the disruption budget and take manual action on that. That has never happened in production, and hopefully will never do. And there's also some field that we've added to the XPod cross-cluster pod disruption budget resource, which is a suspend field, which is similar to the Flux suspend field, where you can just simply disable that resource temporarily. So in a local cluster, you can then continue to delete pods if you're really sure that this does not cause any issues. All right, there are a couple of more things on this topic which have previously been presented at KubeCon. One talk by Ilya Chekrygin. He also has implemented a distributed pod disruption budget thingy. Unfortunately, it's not open source, but definitely worth a watch, that talk. And also some talks related to how to carefully replace nodes across multiple clusters that helped us to optimize our node management. All right, so if we're lucky, we can get this demo running. Let me see. Oh no, I cannot move it. Ah, there we are. Oh, we are not. All right. All right. It's just pre-recorded, so all right. Oh, it does not work. Oh no. Oh no, oh no. Let's see if the scaling works now. No. That looks okay. Okay, so on the right-hand side, you can see GKE. On the left-hand side, you can see EKS. So we have CockroachDB, 4 pods in each cluster. So on the left, at the top left-hand side, I try to delete a pod in EKS. On the right-hand side in GKE, I try to do this simultaneously. So I trigger the pod deletion in GKE, and it goes into terminating state. And on the left-hand side, let me pause quickly here. You can see that XPDB denied the request because we cannot disrupt this pod because it's unable to obtain the log. So this is like pretty much the race condition that I've talked about. So that prevents that pod from getting deleted. Now we can just try to delete the pod every 2 seconds, and we can see a similar error message now where it says we cannot violate the pod's XPDB disruption budget. So on the right-hand side, you can see in GKE, CockroachDB 0 is about to come up. 2 out of 4 containers are ready. The pod is running and should be available soon. And as soon everything is ready again, on the left-hand side, we should see that CockroachDB 0 gets deleted in just a few seconds. All right, so CockroachDB 0 is now terminating. And now let's try to delete it in GKE again. And as you can see, we cannot do this because it's in terminating state, so it's not available. And with that, that's it from me. Thank you very much. Are there any questions?
How do the XD or the cross-cluster PDBs instances in each cluster communicate with each other?
How? They use gRPC to.
So they have to go via ingress or flat network or something like that?
We have flat pod network between the different clusters, so they can directly communicate.
Can you configure it that you don't need a flat network, that you have something like over-dedicated load balancer communication?
Yeah, sure.
Okay,
Yeah.
it's not bounded.
It's just a TCP port that runs gRPC, and then you can just have your load balancer or make it public. Do whatever you need to do to make it work. Yeah.
I mean, public internally.
Yeah.
Okay, thanks.
Yeah, sure.
Any more questions? Yeah.
Have you considered trying to using something like etcd in favor of the leases to actually hold the log of hold the distributed log across the clusters instead of relying on native Kubernetes objects?
We haven't considered it because we are running a managed control plane. So we run just EKS, GKE, AKS, and everything is managed, and we don't want to or need to run etcd on top of that. It's quite complex.
You don't want to deploy your own etcd, it would have the same problem as the CockroachDB, basically.
Yeah,
right?
That's true. Yeah, that's true. Yeah, sure. It's a stateful workload then as well. Though it can be cluster local, so it's not that you have But I guess you can have like different topologies. There are like multiple ways to do it. But yeah, I would rather not have another stateful workload that we need to manage. And I don't even know what the state of etcd operator is. I don't think it's maintained anymore. So it's not as simple to run etcd simply.
Okay. Yeah.
Have you tried to get these changes upstream into PDB?
No.
Because it might be worthwhile.
Yeah, so we took a look at some alternatives, and all of them pretty much involved to disabling the PDB controller. And this flag is not available with managed Kubernetes that you have. So in EKS, GKE, AKS, you just cannot configure that field, because then we could have implemented our own controller and make it aware of everything across multiple clusters, but so we don't have access to that. Not sure if it's worthwhile to implement it, honestly.
Yeah, just maybe if they could somehow make it a little more extensible so that you could kind of plug things like this into it, might be worth considering.
Yeah.
Alrighty. If there are no more questions, so there is a break now until